Hello everyone and welcome to AISC's webinar, Practical Implementation of Composite Floor Designs, presented by William Jacobs. Today is February 18th, 2016. My name is Christina Harbour and I'm with AISC's Continuing Education Group. I'll be moderating today's presentation. I want to introduce today's speaker. William Jacobs is a principal at Stanley D. Lindsay & Associates in Atlanta, Georgia, where he has been involved in the design of building structures and erection planning throughout the Southeast. He is a member of the AISC Committee on Specifications, AISC Task Committee 5 on Composite Design, and the AISC Committee on Manuals. He is the primary author of the composite design examples that accompany the Manual of Steel Construction. Mr. Jacobs also serves on several AISCE committees and is a licensed professional engineer in 7 states. Welcome, Will, and I'll let you take it from here.
Thanks, Christina. I appreciate it. Again, my name is Will Jacobs with Stan Lindsay & Associates, coming to you from my office in Atlanta, Georgia. And today we're going to be talking about the practical implementation of composite floor designs. Now, this is actually an encore presentation of a session that was given as part of AISC's Night School, I believe Night School 8. So for those of you who are also registered for that, this should be old hat to you, and you must either really like composite floor design or in desperate need of PDHs. But in any event, welcome back. And for the rest of the new people, hopefully you'll be able to pick up some useful information as I'm going to be presenting on a few topics and situations regarding composite floor designs that appear rather frequently in the field but are not very well addressed in the current codes or specifications. So the talk's going to be broken down into 3 parts. In part 1, I'll discuss conduit within the slab and then penetrations and openings through the slab. I'm not going to be discussing openings through the web of the members themselves. That's addressed quite nicely in AISC's design guide on web openings. Then in part 2, we'll talk about the strengthening of in-place composite beams, addressing such topics as do you need to relieve the load on the beam before you weld on your reinforcing plates, the effect of welding on an in-place beam, things like that. And then we'll wrap things up in part 3 with sort of a hodgepodge of best practices and 10 tips for composite floor designs. So in part 1, again, we're going to look at conduit, then penetrations and openings, the impact that penetrations and openings adjacent to a composite beam may have on its effective width, and then a couple of special cases. So when I think about conduit, I think about this situation. Hopefully you have not found yourself here, but this is actually on one of my jobs, and I went out onto the job site and ran into this situation. So if you look, you can actually see that there are indeed shear studs poking up between this mass of conduit. And unless that conduit has some redeeming structural value of which I am unaware, that beam is most definitely no longer composite. That slab itself is also in a good bit of trouble. All right, so this is obviously one of the extremes, and here we had to do a lot to fix it. We had to spread out the conduit, add in some additional filler beams, reinforce the slab, put a cover plate on that girder that was supposed to be composite. So a great deal of fixing involved. Hopefully you don't get to this point, but there are situations where you need to have conduit within your slab for all sorts of different reasons. So what amount of conduit is reasonable? What can you tell the contractor is okay? And then in conditions where you do have to bundle some conduit, what can you do about it? All right, so the first thing I want to take a look at is, are there any actual codes and specifications that address this particular situation? Back in 1991, AISCE 3 released the standard for structural design of composite slabs. This standard is retired, so it's no longer a legal standard. However, it was a pretty good resource, and it did have some recommendations on conduit spacing. So what I've done is I've taken those recommendations and placed them in graphical format, and it looks something like this. So here you're allowed to have a minimum spacing between conduits of 1 foot 6 inches. You can have a maximum diameter of conduit of 1 inch or the thickness of the concrete cover over 3, and you can't have any conduits cross over each other. All right? So if you can get a contractor to always follow this, then you are a better engineer than I. But at least it's a baseline, right? It's something that I can recommend you put on your general notes or a typical detail in your drawings to say, you know, this is something that I am okay with as the engineer of record because it does not affect the performance of my composite slab or composite beams. Right? Then if you run into situations that go beyond this, you have to address them sort of on a case-by-case basis. But again, this comes from a standard that has been retired. So the question is there any sort of more modern standard that you can reference that people can get their hands on? And again, the answer to that is yes. Steel Deck Institute in 2014 released the Floor Deck Design Manual, first edition. So there was approximately 25 years or a quarter century for them to perform some hardcore conduit research and gain some additional knowledge of this behavior. So let's see what they have to say in graphical format. And the answer is absolutely nothing has changed. So they give the exact same recommendations that were in ASCE 3, 1 foot 6 inch minimum. One thing they did do, so some progress I guess was made, is they clarified that you need a 3/4 inch minimum cover below the conduit as well. And that's simply to allow the mechanical interlock between the concrete slab and composite deck to take place, so you get the composite action within the deck itself. So in cases where you want to put conduit closer together, or where you have to, there are a couple of different options. One of them is to simply reinforce your slab as a regular reinforced concrete slab per ACI 318. I'm referencing ACI 318.11 here because everything moved around in 14, and honestly I haven't figured out where everything went, so we'll go with this. So if you take ACI 318's recommendations, again put them in graphical format, you get a huge boost in terms of minimum spacing. So you can go all the way down to 3 diameters between conduit at the penalty of having to reinforce your concrete slab and meet ACI 318 limits for shear, flexure, minimum reinforcing, things like this. So this is something that you probably want to think about pretty hard before having to go down this route. Right? But what if instead of just a couple of conduits that you have to deal with, you have a whole slab of them? For instance, in a radiant heating pipe situation where there's a mass of conduits or pipes going back and forth. There's really no recommendations for that I could find on this side of the pond, but there are over in Europe. Steel Construction Institute, which is ACI's sister organization, produced a technical note 350, which is given from the URL on this screen, that addresses a lot of situations that come up with a heating pipe situation. And really this is very applicable to closely spaced conduit as well. So it's a pretty good set of rules for you to follow, and I'm going to go over them. One thing I should say starting out is that SDI's recommendation is to install the radiant heating pipes in a non-structural topping slab. Okay? So you just bypass the issue altogether. I think that is a great way to go, but if you can't, then you can follow these rules. So the rules go like this. Place the conduit or pipe a minimum of 1 inch above the top of the metal deck surface. That's versus the 3/4 inch in ASCE 3. You should avoid longitudinal conduit within 8 inches of each side of your composite beam center line. Where you do have conduit or pipes running across transverse the beam, you should put them in the outer thirds of the span. That's just to get them out of the middle portion of the span where the compressive force in the slab is the highest. When you run strength calculations for your composite beam, you would then ignore the strip of concrete that is displaced by the pipes in the calculation of your compression block. And I'll show that visually in the next slide. And then finally, you would consider studs, shear studs, that are within about 1.75 times the stud height as ineffective. So I generally take this as about an 8-inch radius circle. If you have a conduit crossing the beam anywhere within 8 inches of a stud, you would discount that stud within your sum of QN calculations for your beams. So here is a diagram of this pictorially. You want to keep a longitudinal conduit without or outside of this red zone, 8 inches of each side of the member. You would also discount a stud if the conduit passes within 8 inches. And then over here in your compression block, you leave out this little piece of slab, so your compression block would get a little bit deeper when you're doing your checks. So again, this is a lot of extra work to take all this into account, but if you do need to have a large amount of conduit in your slab, it is an option that is feasible for you to implement. So summary advice for conduits. I would place the SDI requirements for minimum spacing, maximum sizes, etc. directly on your drawings as a baseline. If denser conduit is required at specific locations and you're not needing your full composite action, you can place the transverse conduit in the outer third of the beam span. You would design beams that have a bunch of conduit, such as that opening picture I showed as non-composite is certainly the easy way out. And in places like junctions where a bunch of conduits come together, you would just design those as openings within the slab itself. If you have a dense conduit layout and you must achieve your composite strength, one option is to reinforce the slab in accordance with ACI 318. You would then discount the studs near conduit within 8 inches of it, and you would remove that piece of the compression block in your calculation of your flexural strength. Okay, so that takes us to penetrations and openings through the slab. So again, when I think penetrations, I think of some of my jobs where I've gone out in the field and see things like this. I do not consider this several penetrations. This is one penetration that they just happen to make by sleeving something 10 times. This is not even the worst case on this one job. I think the winner was here, where it appeared that they cored, I believe, 16 times in a row, right in the center of this slab span, so essentially making the slab cantilever over from this beam and cantilever over from this beam. So not a good situation. We ended up having to put in a post-installed steel frame to handle this. So again, this is not where you want to be at, but you do want to have some rules to address situations for penetrations. I would recommend having a minimum spacing between cores of at least 1 time the diameter of the core, as well as specifying that you shouldn't cut adjacent deck flutes if at all possible. There's a good deal of guidance out there regarding penetrations through the slab. There's some more practical guidance as well as some ideas for how to reinforce the slab. OSHA Regulation 29 CFR Section 1926754E2 2003 discusses it, as does SDI's Floor Deck Design Manual, and SDI wrote a white paper in '87. It was updated in 2000 that discusses some options for reinforcing around penetrations. So we'll take a look at each of these in turn. So OSHA regulation is essentially common sense. It says that your roof and floor holes and openings shall be decked over until essentially immediately prior to being opened up for whatever pipes, etc., need to go through them. And this is simply a safety consideration for the workers. They don't want to step through a hole. SDI is a little more clear in that they require in their floor deck design manual that you put in a pour stop, you place the concrete then achieves 75% of its design strength, and at that point in time you field cut the deck after the concrete pour. You don't cut it ahead of time. And that's simply because the deck wasn't designed to have a hole in it for the wet weight of concrete. So you want to go ahead and use all the strength of the deck that you can for the resistance of the wet weight of concrete, and then come back and cut out your opening at a later time. For cases where you need to reinforce the deck, SDI recommends that you weld on a gauge plate to the bottom of the steel deck for when the opening is up to 13 inches. And then for openings that go all the way up to 2 feet, they recommend that you weld C4s onto both sides of the opening. I've never seen this done in practice. I guess you could come in and do this if you didn't know where the opening was going to be ahead of time. But if you do know where the opening is going to be ahead of time, it makes far more sense and is far more economical, in my experience, to simply add reinforcing within the slab. So let's take a look at that option. What's shown on the screen here is more of a crack control layout for reinforcement, where you are extending bars and turning them past the corners, the re-entrant corners, to keep the cracks from opening up. But there are cases where the opening is large enough that you need to actually place flexural reinforcement on both sides of the opening. So there's always been a question of, what exactly do you assume in terms of an analytical model to be able to really look at this in depth. And again, SDI to the rescue here with their floor design manual. They provide sort of an analytical construct in order for you to take a look at whether your deck needs to be reinforced or not. And what they recommend is essentially just an in-slab fake beam and girder system. So what you're looking at here is a plan of a composite floor. You have a steel beam support here and a steel beam support here, with your opening, in this case, in the center. And they recommend that you analyze fake in-slab beams that are 2 times the concrete thickness and width on each side of the opening for a uniform load, and you put in a piece of rebar as necessary to carry that load over to then point loads at these 4 locations, which is resisted by an in-slab girder. And that girder is a little bit wider. They say to use 2 times the thickness of the overall slab depth, so the concrete plus the deck thickness for that slab girder width. So let's take a look at an example and see how that works. So they used a 2-inch 20-gauge deck with 3.5 inches of normal weight concrete. In this case, the dead load is 50 PSF and the live load is 50 PSF. This equals ultimate load of 140 PSF. Your fake beam width is 7 inches from 2 times the concrete thickness. And so you look at half the tributary width of this section over to the beam. So that equals 3 feet over 2. That gives you 210 pounds a linear foot. And from there you can use our good friend statics to calculate the moment and shear capacity, or demand, WL squared over 8. And that gives you 0.105 kip feet and 0.210 kips that needs to be resisted by this concrete. So there's a couple ways for resistance. You can go ahead and design a piece of reinforcing to handle it, or if you so desire, you can look at ACI's provisions for plain concrete to see if you can get out of putting the reinforcing in there altogether. So that's what I did in this case. You run through this fine equation from ACI. What you'll determine in this particular instance is indeed the plain concrete is adequate for the flexural and shear resistance, so you really don't need any reinforcing at all for this slab and opening layout. So that takes care of the little red beams. Now we got to take their reactions over here and here to this in-slab girder. And again, just use statics to come up with your moment of WL squared over 8 plus P times A. And then you can back out what the uniform load is on that girder so that you can just open up a deck catalog. So in this case, we backed out using the inverse of WL squared over 8 that we needed 107 pounds a linear foot, and our girder width happened to be very close to a foot, so that 107 pounds a linear foot just translated to 107 PSF, and from the deck catalog, our allowable was okay. So after going through all that, what we determined was the slab and metal deck is just fine without any additional reinforcement. So in this case, I would still go ahead and put rebar around for crack control, just a 1 number 4. But I would recommend that you go through this for your typical situations, slab thicknesses, spans, loadings, etc., and create typical detail for your firm to see what type of reinforcing you would recommend be placed. There comes a time when the opening is large enough or there's heavy enough loading that you need an actual steel support frame. In this instance, I normally do about 2'6" or 3 foot as the maximum opening I would really think is a good idea in a composite slab. And what I say here is that you can omit the side beam, which is, say, this beam over here, if you can design this piece of the slab to cantilever over from this member. So once this distance gets below about 1'6" or something like that, I generally omit this one beam altogether and just have a 3-sided opening. They also make pre-manufactured steel frame supports that you can stick up under an existing slab that connect under the flutes onto the top of the beam, so that is a possible solution if you're looking to post-install something. So as a summary, for penetrations and openings, you should specify that the deck openings not be cut until the slab reaches 75% of its design strength. It's most economical to provide in-slab reinforcement where you know where the openings are going to be. It'd be a good idea to just go ahead and go through that model I showed to create reinforcing details for your typical slab types and loadings. You should specify a minimum spacing between penetrations to try to avoid the situation I showed in the opening picture. Add your support frames as required. And one piece of advice that I think holds true for most everything is to go out to the field. If I hadn't have gone to the field on those 2 jobs, that conduit would have just been covered up in concrete and I never would have known the difference. Hopefully there wouldn't have been a problem, but there could have been. So you never know what you're going to see. I would recommend you get out there before that concrete's placed. And finally, you need to pay attention to the effect that penetrations and large openings have on composite beams, which is a blatant segue for our discussion on the impact on effective width. So as a review, effective width is just taking a nonlinear stress that's present in your beam flange and treating it as a uniform stress. So basically just a concrete compression block. So you can see here that the best place to put an opening would probably be out here and out here, sort of in the middle of the slab between the beams, because that's the place of lowest stress, in addition to toward the support of the beams. So that's what I say here in your first note. The least theoretical impact is near the support, midway between the beams. For penetrations up to about 12 inches, I ignore them. They're generally not significant, and we're just not that good. They don't impact your design. For larger penetrations, you can take a look at a paper by Ken Weisner from Modern Steel Construction in 1996. He recommended that openings located at the ends of beams less than 1/8 the distance to the maximum moment, which works out to be a span over 16 for uniformly loaded beams, can be completely ignored in terms of their effect on the effective width, as long as they are at least 6 inches or L/80 away from the beam center line. So that's another time where you can ignore them entirely. But there comes a point where there are openings near your beam that you cannot ignore at all. For instance, this particular situation. Here you're looking at a plan. There's a composite beam in question here, and we have an opening that's a distance A from the center of the beam up here, and an opening that's a distance B from the center beam down here. So what I would do in practice is immediately check the beam with an effective width of A plus B. And if that beam works with that effective width, then you are finished and you can move on about your day. But there comes a point in time which perhaps that beam was already fabricated, it's already erected, and the HVAC guy just figured out what size unit they're going to put, and they need to put some giant openings right next to your beam that you weren't aware of. So you might need to sharpen your pencil a little bit and see if you can get some more out of that slab. So in that same paper, Mr. Weisner recommended taking a look at it like this. So what he did was say, all right, the specification says that your effective width can go all the way out to the span of the beam over 8 to each side of the center line. So that would be represented by this F and this G value. So if I look at the effective width as emanating outward from the end of the beam to span over 8, this alpha angle is calculated as 14 degrees. So he said, I'm going to take that same alpha angle and just apply it to the spring angle of the effective width beyond these openings. So what I mean by that is a diagram like this, where you come down the width of the opening and then you spring out by that same 14 degrees. And you go up here and you spring out by that same 14 degrees. So what that results in is an effective width zone that sort of has a kink in it and looks like this. So now instead of just A plus B, you have an effective width of A plus B plus this spring angle, 0.25, times the distance between the openings, which is a fairly significant increase depending on the geometry and location of the openings. And then you have to check the demand of the beam at the sections at the opening and at the point of maximum moment. Now there is a caveat here because you have a kinked section in your analytical model. What Mr. Weisner recommended was you calculate the compressive force at the centroid of your effective width, shown here as F1 and F2. And each of these have an eccentricity to your beam center, shown as E1 and E2. And he recommended you calculate what moment results from that within your slab. And then that moment can be resisted by a force couple in the slab, shown here as F slab 1, F slab 2. And those forces can be resisted by additional tension reinforcing that you place within the slab itself. Right? So you get a little bit of extra effective width at the penalty of having to put some reinforcing in your slab. If you're going to do this method, I recommend you read his paper because there are a couple additional caveats and some design examples that will help you make your way through that solution. Okay, so let's take a look at special cases. These really aren't that special because they seem to happen a lot. The first one would be what actually happens when you have an opening that crosses the beam itself. So you have a section of the beam that has no slab on it. Or perhaps even more common is when the slab itself is held back from the end of the beam, as shown at the bottom of the screen here. So you have a segment that has no slab on it on this side and a segment that has no slab on it on this side. Now you know as an engineer that this portion in the middle is going to do something. It's going to help you to some amount. But if you are designing this in a program, say ram steel or something like that, the second you have 1 millimeter of beam that sticks outside of a composite slab, it will say that beam is non-composite and you get no effect of the composite action at all, which is an excellent conservative approach. But if you want to try to sharpen your pencil a little bit, you can look at something that I call the sectional approach to see what kind of capacity you can still get out of this beam. And in order to demonstrate the sectional approach, I'm going to spring off of AIC design example I-1. This was just a typical 21 by 50 uniformly loaded beam. It ended up with 42 shear studs on it, and the moment capacity was 670. The demand was 678 kip feet compared to the capacity of 769. Right? So reasonably designed beam. And what we normally do is we calculate the capacity, 769, and if you look at our demand here in the center of the beam for a uniformly loaded beam, there was our demand, and the capacity meets the demand. So we're good to go. Right? But what if you wanted to know what the capacity was, say, at the 10-foot mark, or at the 5-foot mark, or closer to the end of the beam? How would you determine that? For a uniformly loaded beam, you don't need to, but just out of general interest. Stick with me here. So what we would do is we would do a sectional approach. And all that is cutting a section at each one of the shear studs and summing the QN on each side of that section. And the smaller value from each side of the section is the controlling sum of QN for that particular section. So for instance, if I made a cut here, I would say, all right, I have 1, 2, 3, 4, 5 studs to the left, and 1, 2, 3, 4, 5, way more than that to the right. So my sum of QN for this particular beam section is based on 5 studs. And I could then go in and calculate the flexural capacity of that member for a sum of QN associated with 5 studs. And then I could move this section cut over to the right and do the same thing, except then I would have a sum of QN based on 6 studs, and 7 studs, and 8 studs, and so on and so forth, until you end up with a stepped capacity diagram as shown here in blue. So this diagram represents the actual capacity of that beam all the way along. So again, not necessary to do for most general cases, but you can use this tool to take a look at some of these special cases. One thing I'd like to point out is when you design a beam right to its capacity. So let's say you're a very progressive designer and you end up with a moment capacity and demand equal, you end up with this teeny little zone that this method of sectional cuts would call unsafe. And that's not true. Again, we're just not that good. Safety factors, assumptions, etc. Are enough that you can ignore that tiny little issue with this particular method. Another way that you can go about this, which is even easier, is to just draw a straight line between the non-composite capacity of the beam and the composite capacity of the beam. So you're leaving a little bit of extra capacity on the table between that red line and this blue step diagram, but again, in many cases, it's not worth the extra hassle. All right, so let's bring this back full circle to our current situation where we have a slab opening on one side of the beam and our slab step back on the other side. So in this case, if I make a section cut in the exact same location that I did last time, instead of having 5 studs to the left, I only have 1. So my sum of QN is much less. And then for the next case, I have 2, 3, 4, etc. So let's take a look at that particular step diagram. So here is the original diagram in blue, but now my new diagram in red shows a non-composite capacity over to 5 feet, and then it steps up and falls back down. So in this case, our beam would fail quite spectacularly. So there's a couple things you could do with this particular beam. You could just choose a bigger beam. You could size it based on non-composite action, or you could go in and put in additional shear transfer. So let's say instead of 1 stud per foot, I had 2 studs per foot. So you'd go in and recalculate the capacity, and it would look like this in purple. So here we gain quicker, and we're able to go up and over the required demand. So this is a case where you could certainly use that beam and use its composite action to meet the demand, even with slab openings at both ends. Okay, so take us back to the initial diagram that we looked at, where we have our nice moment capacity and we just look at the demand here in the center. And that works fine for a standard beam with uniform studs. But what if you had something like an uneven stud distribution, where you have, say, twice as many studs on the right half of the beam as you did on the left half of the beam? What effect might that have? Again, same thing. You can just cut sections and sum up QNs left and right to create yourself a stepped diagram. And in this case, the stepped diagram has a peak that's shifted over toward the side with more studs. It doesn't help you at all for a uniformly loaded beam because you're still have a maximum moment in the center of the beam. But where it might help you is a case like this. Let's say you had a point load at one side of the beam so that your moment diagram was skewed. And this is actually addressed already in the specification, where the spec requires that the number of steel anchors between any concentrated load and the nearest point of 0 moment shall be sufficient to develop the maximum moment required at that concentrated load point. So in essence, that's what they're doing. They're shifting the capacity diagram of the beam over to encompass the moment at that point load. Okay, so that takes us through part 1, conduit penetrations and openings. And now we're going to jump right into part 2, composite beam strengthening. I'll answer questions on all 3 parts at the end of the presentation. Okay, so for part 2, we're going to look at general issues. Why you may strengthen a beam in the first place, what resources are out there available to you, and options for reinforcing. Then we're going to take a look at strength issues, such as the effect of load history on the beam. Do you need to unload it before putting on your reinforcing? Can you mix steel grades? Can you put a grade 36 WT on a grade 50 W shape? What effects welding might have on the beam? How you attach the reinforcement and rules for that. Then we'll talk about minimum composite percentages and actually how to calculate the flexural strength for a composite beam with a cover plate or a WT. Finally, we'll finish up with serviceability issues, the effect of load sequencing on deflection, and how to deal with partial length and non-prismatic type member deflection. So first of all, why strengthen? Generally, we do this when there's some sort of a change in use. Let's say you had to change an area to an assembly area, or perhaps you have a foul load that is being added, so you have additional not only dead loading but much more stringent deflection criteria to try to keep the tracks of your foul loading system from binding up. You might also have some vibration criteria that were not originally met. And all of these things are good reasons to strengthen, but I would also caution you that strengthening is generally fairly expensive. So the first thing you might want to do is look at a change in the load path. You know, if you can move that file system over closer toward a column, or if you could put a post in to try to get that load down to a stronger member. So anything you can do to avoid strengthening, you might want to. But again, this is a presentation on strengthening composite beams, so let's assume that you've exhausted your options and you need to go in and do something about it. There are a lot of resources available for composite beam strengthening. Probably the two best ones are Bo Dowswell's series of live webinars from AISC. They are free on their website, so you can go watch them at any time. He talked for almost 3 hours about reinforcing members. I've got about 30 minutes here, so obviously there's a lot on this topic that's out there. Highly recommend you go listen to those if you find yourself in this situation. Mr. Miller wrote a nice paper in 1996 that gives some examples of strengthening composite beams and some nice tables. David Ricker wrote a great paper on field welding to existing steel structures. And finally, AISC has some design guide and specification information that you might find useful. All right, so you're going to go about reinforcing, and the first thought is, what kind of reinforcing should I put on there? Should it be plates, WTs, something else? So let's take a look at our possible options and the advantages and disadvantage. The first option, probably the most common option, is just to weld a plate to the bottom of your beam. This is a great option for members that need just a little bit of additional capacity. There's a couple of benefits. You have downhand welds here and here. Normally a welder can accomplish a downhand weld about 4 times faster than an overhead weld. It's also nice because you can clamp this plate to the bottom section of your beam to be able to accomplish that welding. Right? So it's erector friendly. Again, the disadvantage is you don't get a whole lot of extra capacity. So when you want to add a bunch of capacity, most engineers that I've run into would think about adding a WT, because that's the most sort of engineering-y solution. It adds the capacity where you need it. It puts a bunch of steel out farther from the neutral axis of the beam. So that's great from an engineering perspective, but it causes a lot of issues from the erector perspective. You have to perform this overhead weld, for one, which is difficult, and for two, how do you hold this member up there in order to complete the weld, just in terms of feasibility of implementing? Erectors can do it. I mean, I've seen them, but it's not particularly easy. So what I recommend doing is adding a W section, like a W8, W10, something like that, where you need a lot of additional reinforcement. And this sort of has the best of both worlds in that you can clamp the member to the bottom flange temporarily. You get a downhand weld if you size the W shape correctly to be wider than the flange of the existing beam. And you also still get your material hanging way out here for your calculations. If you're being judged by every pound, obviously this does add more material to the job. But if you're in a design build situation or you're actually working with the erector, then this would definitely be an option to throw out there. Some considerations, site and member access and constructability. So what I mean by this is normally in a reinforcing situation, you're probably working in an existing building. You might have limitations in terms of how big of a piece of reinforcement you can put in a freight elevator. You might be reinforcing a member at the edge of the building where you can only get at it from one side, so you need to do a reinforcing piece with a one-sided weld only. You need to consider fit up. If the current beam that you're trying to reinforce has a very large deflection, it would be extremely difficult to get, say, a W8 or a WT to fit up against that member without jacking out the current load on it. And finally, something that you might not think about is to actually review the existing connection strength. So a lot of times we spend a lot of effort in doing all these flexural deflection calculations, and we forget to go back and make sure that the connection is good for the shear. Okay, so that's the option of putting some reinforcing from below, but what about adding additional shear transfer? This is much less common, but it is certainly feasible. The image on the left is a picture from Ricker's paper, and the image on the right is a picture from Hilty that shows coring down through an existing slab to the top of the beam and adding in additional shear transfer. I would really recommend only doing this in extreme situations or situations where your beams were designed to be non-composite in the first place. So you're actually adding composite action to a non-composite beam supporting a slab. And the reason behind that is twofold. First of all, if you're trying to add additional cores to a beam that's already composite, it's very difficult to avoid all of the existing studs when you're coring down into it. And secondly, you're really not going to get a lot of bang for your buck, because if you're already at 50% composite, say, the additional flexural strength you get by having to add enough studs to get you up to 80% composite is really not a whole lot, because that curve flattens out after about 40%, so where you don't get much more flexural strength from the addition of studs. But if you do want to do this, it's best, again, for creating composite action in non-composite beams. This is a good idea if you can only access the top of the member and not the bottom of the member. When you do it, you should utilize non-shrink grout of the same or greater strength than the in-place concrete. Some sort of gotchas are that it's difficult to test the studs. It's hard to perform a bend test in the middle of a 4-inch hole. It's messy. You have to core these holes, which requires some sort of water or lubricant for your core drill that may be an issue in an existing space, as well as the fire hazard that's caused by having to weld the studs down. And that's where alternatives to studs come into play. So there's a couple of options other than using a traditional shear stud. A lot of these options were tested for bridge retrofit work for the Texas DOT. I listed 2 references here where they tested all sorts of things. They looked at through bolts, at screw anchors, at adhesive anchors, basically any option you can think of, they retrofitted a beam with it. So those are some good resources for that. And finally, Hilty makes something called an XHVB connector, which is this picture shown in the bottom right. So they're these little S-looking things, and they can be shot down into your steel beam using pneumatic fasteners. So it gets rid of the bend test issue and the fire hazard issue. These aren't explicitly covered in the specification, but they would be allowed as a special alternate, assuming that your building official will sign off on it. Probably the wildest solution I'll show is external post-tensioning. I've never seen this done in a building, but I guess it's possible. I've seen it done on bridge work, such as shown here, and the idea is you're just taking some post-tension bars and compressing below the neutral axis of the beam to reverse camber that member to provide additional load carrying capacity. Again, not a very common option. Okay, so now let's take a look at strength issues. Composite beams are at a major advantage when it comes to looking at load history, and that's because they are braced against flexural buckling by the composite slab. Right? It's very nice to have. Also, all composite beams or all W shapes currently meet the criteria for compactness that's present in Chapter I. So the beams are braced, all W shapes are compact, and therefore you're able to develop the full plastic strength of the section. And for a plastic stress distribution, the load history has absolutely no effect on the available flexural strength of a composite member. So that means if your member is already stressed all the way up to, let's say, first yield, and you go in and you add a WT to it, assuming the connection between the two is adequate, you can continue to push that member all the way up to the plastic strength of the combined shape with no worries about the load history. And that's due to the extreme ductility that's present in steel. So a quick refresher course in ductility. The strain at yield is given by Hooke's law. For 30 KSI steel, we're at 0.0012 inches per inch. So that's way down here. And then the strain at the end of the yield plateau over here is about 12 times that yield strain. Right? So you already have a good bit before the member starts to strain harden. And we normally look at these in terms of a elastic perfectly plastic diagram as shown by this red line. So you ride up your elastic zone and then you plastify and you ride along your plateau here until finally you reach the maximum strain allowed by ASTM, in which case your member would rupture. For that case, for A36, the rupture strain is 0.2, so almost 200 times the strain at yield. So you have a long way to go before you fall off the end of this cliff and rupture your member. So if we take a look at a composite beam, let's say this beam has the bottom flange already loaded up to 30 KSI or so, as shown by this green dot here. And then I came in and I put a WT on it. And I continued to push on the member. What would happen is the stress in the bottom flange of the original member, this green dot, would just go up, it would yield, and it would start to travel along this plastic plateau. Meanwhile, our orange dot, the strain in the bottom of the WT, it would start to creep up, creep up, creep up. So as long as you can get all the way up to here and yield that stuff, that steel, without this green dot falling off the end of the cliff, then you can develop the full plastic capacity of the section. And that is pretty much always going to be the case. Again, you've got 200 times the yield strain to work with. And I knew that intellectually. I mean, I knew that to be the case, but I've always wanted to sort of take a look at an exercise to prove it to myself. So that's what I did for this presentation. So what I did was I took a pretty hefty built-up shape, and I said that it was stressed all the way up to first yield. So the bottom flange here is stressed all the way up to 50 KSI. And that strain over here happens to be about 1% of its rupture strain. So what I wanted to do is say, okay, if I weld on another member that's as big as the first member, so another huge built-up shape, and I continued to add load to this system until I yielded the entire cross-section, at what strain would I be at? Like how close would I actually be to rupturing any part of the member? So we're going to go through that right now. So we add this second member. We say that it's fully connected, 100% composite. And I start loading. And the first thing that happens is you start to plastify, shown by this red zone, the top of the initial member. And again, you start getting stress and strain down at the bottom of your new member. So let's keep loading. Our zone of plastification at the top member gets even larger, and our stress and strain at the bottom member gets even harder, or gets even higher. So now you're at 50 KSI at the new member, but we're still only at about 1% of the rupture strain. And we're already up to 87% of the total plastic capacity of the whole member. Right? So we still have 99 times more strain to get to before we have any issues. Keep pushing. Now you're starting to yield the lower member. And at this point in time, you are at 97% of the plastic capacity of the total section. And again, your maximum tensile strain is only at 10% of the rupture. So you're nowhere near causing a rupture issue in this massive built-up section, even though you added the same amount of steel onto what you already had that was initially already at yield. So it's just not an issue. So you can keep on pushing until you get the whole section plastified. So mixing steel grades. Can grade 50 material reinforce grade 36 material and vice versa? And again, the answer is yes, as long as you can assure this plastic stress distribution is valid. And that's for the exact same reason that load history is unimportant for strength. That being that steel has enough ductility to allow mixed materials to both yield. So if we review the same sort of double stacked W-shaped thought experiment as before, with the same preload, but now the bottom member is A36 rather than 50. I won't go through the load history because the idea is the same, but this is just an intermediate point where we're yielding the bottom member up to 36 KSI, and the top member is being yielded at 50 KSI. And if you push this all the way to failure, your maximum tensile strain is 17% of rupture. Right? So even though I put on a grade 36 member to a grade 50 member, I was able to achieve the full plastic capacity of the section without any worries about rupturing the overall section. This has been borne out in a lab test. Here is an example. For this particular case, this was a simply supported beam where they added on a reinforcing plate prior to adding any load, as well as after adding both 25 and 50% of the ultimate strength of the member as a preload prior to welding on their reinforcing. So the first test is here in a straight line where the member had the reinforcing added at no load, and then it was pushed all the way up to about 750 kilonewtons. And then this middle line is where the preload was ramped up to about half of the ultimate load before putting on that reinforcing. And then as you can see, it ended up coming all the way up near the original capacity. Same thing happened with the 25% preload. They were able to load it all the way up to the maximum capacity. So again, this does bear itself out in tests. So I keep talking about how this, this load history doesn't have an effect as long as the cross-section can achieve plasticity. And the idea here is you're just meeting the B over T, H over T limitations within Chapter I. So that's less than or equal to 3.76 the square root of E over Fy. So one of the questions is, where did this limit for composite beams even come from? And then how do you apply it to a reinforced composite member? So the answer to where it came from is pretty easy. It came from the table in the SC specification for non-composite members. It's the exact same limit as you have for a non-composite member. And that was based on a stress gradient where half of the web is in compression and half of the web is in tension, as shown here. So as you know, the local buckling effect is a compression-only effect. If something's in tension, it's not going to buckle locally. So the bottom line here is, as long as less than half of your web is in compression, this is a conservative limit for a composite beam. And for the vast majority of standard composite beams, as shown here, you will have less than half of the web in compression because the composite action brings the plastic neutral axis up higher in the beam, so you end up with just this little bit of the web, if any, in compression. So this is a very conservative check for most composite beams. However, if you do add a very large reinforcing section, such as shown here with the WT, it is certainly possible to bring your plastic neutral axis down below the center of the web, so where you have more than half of the web in compression. If that's the case, then you would need to use an alternate limit to assure plastic cross-section that it's compact, and that would be a limit from B4.1 B case 16. At the absolute worst case, let's say you put a humongous member down here so that the entire web is in compression, it would simply be acting as a column, right? You'd have the whole web in compression. And the limit for a column is given here as H over TW less than 1.49. So that's sort of a lower bound worst case. What about flange local buckling? This isn't addressed in the current spec. It's assumed not to control because that top flange is tied into the concrete slab with steel anchors. Way back in the beloved 9th edition ASD book, it was addressed. We said that the steel section is exempt from compact flange criteria and that there is no limit on unsupported length of the composite flange. So that's still the advice that I go by. It's just not a problem for composite members. Okay, let's talk about welding. High temperature reduces the properties of steel. Everybody knows that. Welding produces high temperatures. You know that as well. So consequently, welding reduces the steel properties, at least temporarily. And this isn't normally a problem for most fabrication, but if you are welding on reinforcing to a member that is currently under load, it might be a problem. So the question is how to actually check that. Again, Bo Dowswell addressed this in his webinar in 2014. I'll try to condense it into some usable tidbits here. And the idea is that you use a reduced section. So you see how much of the section that weld renders ineffective. And then you come up with the flexural capacity of the remaining monosymmetric section for the load that's currently on the member when you're adding the reinforcing. So for stick welding, the amount of beam that is rendered ineffective is 1 inch, as shown here and here. So you would check the sort of monosymmetric member for the load on the beam at the time of welding. For a WT, it's a little more arduous because that 1 inch extends both up and to both sides. So you would probably check that WT for the existing load. And the same goes true with a weld across the end of a member. So let's say your termination weld at the end of a flange plate would temporarily render this entire lower flange ineffective. So you would have to take the capacity of this WT and compare it to the loads on the member at the time of reinforcing. If it was not adequate, then you would need to temporarily shore the member prior to adding your reinforcing section. There are a lot of different rules within AISC regarding cover plates. They're in F13.3. They're basically all common sense. They say that you must take into account shear flow, that you need to extend the cover plate beyond where they're actually needed, and that you shall attach the cover plate as necessary to transfer the force between the cover plate and the beam. That's basically all these provisions say. But we'll take a look at what each of these means. And really all we're talking about here is if you have a WT or a cover plate, you need to extend it out this A prime or distance beyond where you need it for the flexural strength of the member. So in terms of the anchorage force that you need to design your plate or WT for, there's two possibilities. There's an elastic cutoff strength and a plastic cutoff strength. So the commentary to AISC F13 gives the elastic cutoff strength as MQ over I. And this is only applicable if your composite section remains elastic. So if your moment is less than phi Fy times Sx of the composite member. This is not common for a composite beam. Normally you are going to be pushing your beam to where some part of it has yielded. So you're going to be looking at plastic design. But just in case, and just for amusement, let's take a look at where MQ over I came from. And it's pretty cut and dry. Your stress in an elastic model is just MC over I. The force in your cover plate is then that stress times the area of the plate. Then if you substitute your stress in here for Fs, you get this expression for the force in the plate. And your first moment, Q, is equal to the area of plate times C. And then you can substitute Q into this F plate expression to finally end up with F plate equals MQ over I as your cutoff force. For plastic strength, the cutoff is simply the full strength of the member that you are adding. So phi Fy Ag. This is what I normally do. You could also perform an elastic plastic analysis to see how much stress actually is crossing that cutoff point with your plastic model. That's as complicated as it sounds, so generally I stick with 0.9 Fy Ag. In terms of the length of anchorage, I tend to not provide an end weld for the reasons stated earlier regarding welding and reduction of capacity of the member in the temporary condition. So I tend to stick with this if no end weld case, in which case your minimum length of cutoff is equal to 2 times the width of the plate. But AISC also provides some other rules here for if you do have an end weld. All right, so that takes care of the extension and the cutoff force. What we haven't looked at yet is shear flow, which we have to address per AISC F13.3. So all shear flow is our mechanics equation, VQ over IT, and you can run through some hoops here and end up with an F weld equals the V at the point you're looking at times your area of reinforcing Y bar of the reinforcing over 2 times I transform. And this is an elastic shear flow model. Again, normally in a composite beam, we're dealing with plastic design, but designing this weld for an elastic shear flow is certainly a reasonable and conservative thing to do. For plastic design, you would generally just design the end of the reinforcing member for the full yield strength of the member as we just discussed, and then you could place intermittent welds, minimum welds in between. Again, I personally think that it's prudent to go ahead and provide the intermittent welds sized for your elastic model of VQ over I. There are a lot of rules for your maximum spacing between connectors and stitch welds. Your S-max is 24 times the thickness of the thinner part joined, less than or equal to 12 inches. And then each of your little welds has to be at least 4 times the leg size, greater than or equal to 1.5 inches. Okay, let's talk about minimum composite percentage. The de facto minimum in the current specification is 25%. There is no actual minimum stated, but that's the minimum that's given in the manual charts, and it's discussed in the commentary. And percent composite is just the sum of QN over your minimum of steel yielding or concrete crushing. And what I'm saying here is you need to be careful for existing composite beams that already have very low composite percentages. If you add a large amount of ASFY, so if you add a large cover plate or W section, you're actually reducing the percent composite action to a point where it could be even below this 25%. And that's not a good idea because studs have a certain amount of slip ductility. And if you exceed that, it is possible for them to rupture and actually unzip. Now, the commentary currently recommends 50% as a minimum composite action for new construction. The 2016 specification that's going to be released soon has a requirement within the specification that stud ductility be considered. And then there are some recommendations within the commentary for how to handle this consideration. And one of the methods is to simply provide at least 50% composite action. So that would be the number that I personally would hold to. This has been shown, again, in experiments. Here you're looking at a load versus deflection curve for a couple of beams. This beam here in blue was non-composite member, so it was pushed up to failure. And then the beams in orange and red were composite members, and they were pushed all the way up until their shear transfer could not handle the ductility demand, so their studs ruptured, and down the capacity goes right back to your non-composite capacity. Right, so that's what we're trying to prevent by having enough composite action to give yourself the necessary ductility. And here's just a picture at the end of one of these tests. So you can see they were testing some fairly large composite members. Okay, so how do you actually determine the flexural strength of a reinforced section? And it's pretty easy. Use some forces in the x direction and use some moments. So step one is to determine the compressive force in the concrete and the depth of the compression block. So that's just the minimum of steel yielding, concrete crushing, or your stud anchor strength. And then your effective depth of the compression block is given by A. Normally your sub QN or your sum of QN value is going to control your beam strength for a partially composite member. All right, so once you get that A, Locating the plastic neutral axis is just a matter of summing forces. So the P&A is whatever location you need it to be so that the sum of compression force in the slab and the steel above the P&A is equal to the sum of tension force. In this case, I have tension in the bottom part of this grade 36 beam and the entire grade 50 WT that I added. So you just move the P&A up or down until C up here equals T down here. Once you've located that point, all you have to do is sum moments, and that equals the flexural strength of the member. So you can sum moments about whatever datum you so choose. Here I summed them about the bottom of the reinforcing member, so I said tension times Y1, tension steel times Y2, etc. You'll get the exact same answer if you sum them about the top of the member or about this point or wherever you feel like it. So pretty easy to come up with the flexural strength of a reinforced member. Serviceability, the effect of load sequence. Really this comes down to whether you want to jack the existing load out of your member or not. Again, if you're not going to shore out or jack out the existing load, you should carefully review welding on the member because, again, it renders pieces of the member ineffective temporarily. And any deflection that is currently in the member is going to be maintained. So really all you're doing if you reinforce a current member without removing the load is you're giving it additional stiffness against future loading, against future dead or live loading. And that's what's shown in this bottom example here. For a uniformly loaded beam, you just get 5W L to the fourth over 384 EI existing for the current load, and then you get 5W L to the fourth over 300 EI of the new moment of inertia for any future loads. And this is, again, if you do not remove the current load. If you want to add reinforcement after the load is relieved, then you get that composite property, that fully reinforced moment of inertia, to be active for all of the load. So whatever load you removed with jacking plus any future load. These days, coming up with the deflection of a non-prismatic beam is pretty easy. You just plug it into a finite element program. But if you are a hand enthusiast, or you just get really excited about things like this, here's an equation for you to do so for a uniformly loaded beam with a reinforced section in the middle. And here is another equation for a girder with 2 point loads and a reinforced section. Again, not something I normally do, but there you go. There are several examples for full designs of reinforced composite beams. I don't have time to go through one today, but Mr. Miller provided one in his AIC paper. Bo Dowswell went through about a 30-40 minute example in his webinar, and Mr. Newman provides a detailed example in structural renovations of buildings. All right, so that takes us to part 3, which is sort of a hodgepodge of best practices and tips that I've picked up over the years for composite floor designs. So our first is fire rating requirements. And this isn't really a tip or anything, it's more of a reminder. And that reminder is that fire ratings are often quite important for our deck. And if you look in the back of a composite deck catalog, you'll generally see a table that has a bunch of things like this. So here, if you want a 1 hour assembly rating and you don't want to have to spray your deck, so you want an unprotected deck, you need to put either 2.5 inches of lightweight concrete over the member or 3.5 inches of normal weight concrete over the member. And it might behoove you to sometimes dig through these UL design numbers to see what actually is included. One of the things that tends to get people a lot is air entrainment. So if you take one of these numbers and you plug it into this database URL, it'll give you everything associated with that particular UL. And again, if you look at one of the more common ones, it'll say here that lightweight concrete needs to have 4 to 7% entrained air in order to meet this UL criteria. Right. We've had some negative feedback from contractors at times for requiring air entrainment and internal conditions, but it is required to meet this UL rating. It's sometimes a little more difficult to finish, can cause delamination issues, but it's certainly feasible, and if a contractor knows what he's doing, it should not be a problem. Number 2, studs help deck 2. So normally the properties given in the deck manual for the allowable applied load onto a composite deck are based on shear bond tests. So actual testing that pushes the slab until there's a break in the bond between the embossments and the concrete. So all composite action is trying to prevent two surfaces from slipping, right? So what we're trying to do is trying to prevent the concrete from slipping along the deck. And one way to help out with that is to weld a stud through the deck so that it traps the deck and the concrete together at the end of that deck span. So several manufacturers have put out alternate criteria that takes advantage of this fact. So here's one from Volcraft, and what they're showing here is for studs that are spaced at 36 inches center on center for a 6-inch slab, 10-inch span, or 10-foot span, I get a superimposed capacity of 255 pounds a square foot. If I reduce that stud spacing from 36 to 24, that number jumps all the way up to 312 pounds a square foot. And then if I jump that number up again, it goes all the way to 397 pounds a square foot. Right? That's some serious load. And you got to be careful about this because it's really important that these studs actually go through the metal deck. So if you have, let's say, a condition where 2 sheets of deck are butted, laps at a beam, you need to make sure, if you're using this 12-inch chart, that you actually have studs welded to each sheet of deck, like on both sides of the lap splice at 12 inches on center. So it becomes somewhat of a issue to keep track of in the field, which is why if I do use this extra capacity, I normally use the 36-inch chart to try to give myself some buffer against having these studs at the correct spacing. Number 3, composite slabs and contraction joints don't mix. When you place a slab on grade, there's very little drag involved. So the slab is free to shrink and crack wherever it wants to. So it makes a lot of sense to put in contraction joints to control where those cracks happen. But when you're placing a slab on an elevated deck, you have a corrugated deck at the bottom of the slab, which has a tremendous amount of drag. So when that slab tries to shrink, it's going to crack all over the place wherever it wants to, no matter whether you put contraction joints in it or not. So they're essentially a waste of time. And what the American Society of Concrete Contractors promotes, and I agree with, is in position statement 23, they essentially say that rather than putting in contraction joints, you should take the effort and money and put it into providing more distributed reinforcement to try to keep the cracks that do form from opening up, as opposed to just putting in defined contraction joints. Number 4, pay attention to deck placement and orientation. So this is a case, again, on one of my jobs where we had a deck that was coming into a skewed beam, and as you can see, they piled these studs into little pods wherever they were able to get them in. What should have been done is a deck closure piece should have been added, and then the studs welded uniformly along the beam. Or even better, we should have just designed that beam as non-composite and recognized that this might be an issue. So just something to think about when you have a skewed deck condition. I've also run into cases like this. For this particular instance, the span of the beam is shown by this red dotted line below, and the contractor welded all of his studs where he could in this nice little zone, one half of the beam. I asked him about this, and he was actually quite proud of himself because in this instance our drawing said 10 studs, and I believe that he had welded 13 down. So he gave me more than I asked for, unfortunately in a quite useless position. Right here is a good picture In this case, we have a member that is parallel to the deck, that the deck did not break over correctly. So there was not a low flute right where we needed it to be. And the contractor cut the deck back off and added a closure strip. So they did a good job. I don't see this happen often, but it's a good way to go about it. I have seen them just drill holes in the top of the high flute and try to shoot studs down through those holes. That is absolutely not what we want to have happen. Probably the best case scenario here was been for us to design this beam as non-composite so that we didn't have to worry about this issue to begin with. Here we have a minimum lateral clear distance to the side of the stud of 1 inch being violated because the deck didn't lap out correctly. So they just shove it over to the deck and shove it over to the stud and try to make it work. So we had to pull the deck off of it a little bit. Number 5, provide minimum flange widths at edge conditions. So what I mean by this is at an edge condition, you're generally trying to stuff a lot of things into a small area. So this is my company's typical detail. So we asked for 1 inch minimum extension of the deck past the center line of the beam in order to give us a lot of room to weld that stud down through the deck. And then we asked for another ½ inch prior to the start of our bent plate to give them room to weld the stop plate onto the top flange. And then you want at least 1 inch land for the bent plate itself. So what you end up with is a requirement for 5 inch minimum flange widths. And so my rule of thumb is anytime I'm on a perimeter condition or an interior opening of any sort of size, I'll use a 14 by 22 or 12 by 26 to give everybody enough room to accomplish all this correctly. One thing you don't want to do is require somebody to notch the horizontal leg of the plate at the location of the shear connectors. These are not my drawings. I apologize if they are yours. But in this particular case, it would have been much more economical to either hold this outrigger plate off of the center of the beam, or if you must extend the outrigger plate, to design welds here and here in order to handle the shear flow between the stud itself all the way down to the top flange of the beam. This actually ended up being quite a mess in the field because they couldn't push the deck down between the areas of the outrigger plate that had been cut out. So in the field they ended up cutting the deck as well, and you ended up with a situation like this, which is just horrible all around. Number 6, slab depressions and steps. So for shallow depressions less than 1 inch, be sure to consider your fire rating. Make sure you aren't violating it. If your concrete cover is enough to allow you to reduce the slab depth without violating your fire rating, then just locally reduce the thickness. Shouldn't be much of an issue. But if that reduction would violate the fire rating, I would either use a thinner deck. So if you have a 3-inch deck on your job, you can locally switch to a 2-inch deck and buy yourself an extra inch for your slab depression. You can also go the route of spray fireproofing the bays that you need to with this shallow depression in order to get around your fire rating. And don't forget to coordinate locations where you might need to use shorter shear studs in order to not protrude from the slab. Where your depressions go up to 3 inches, then you're going to be looking at adding something like a closure angle where your deck is perpendicular to the beam, or just a deck closure strip for parallel conditions. And then when I go above 3 inches for depression, I end up reinforcing nosing bars and crack control bars across that depression with a support angle for deck perpendicular, or some sort of a bent closure plate for the deck parallel. Number 7, account for ponding. And what I'm talking about here is not ponding of water, but ponding of concrete. So when you place concrete on a composite slab, that slab is going to deflect. And if you specify that your slab be placed to a certain level, you're going to end up with some overruns in concrete in order to account for that deflection of the wet weight. AIC Design Guide 3 recommends that you increase the slab weight by 10% to handle this effect. That's something that I do in my practice. And what I've seen is really the majority of this increase is due to the deflection of the members themselves, not due to the actual deflection of the deck between the members. SDI took a look at this. This is from their floor deck design manual. And you can see that even for a 12-foot deck span, some pretty heavy deck, you're only getting about a 3% increase in dead load due to the deflection of the slab. So the majority of that 10% extra is coming from your beams and girders. What we do as a firm is add a note like this to our general notes, which sort of warns the contractor that they're going to have some additional weight due to concrete overruns, and they need to anticipate them in their base bid so that you don't get hit with any sort of add for additional concrete. And for long span systems, I mean, if you're looking at trusses and things like that, you should probably, instead of specifying your slab be placed to a level, you should think about specifying it be placed to a constant thickness, which is a little more difficult to do, but certainly achievable, and that way you don't end up with any type of overrun. Number 8, stud burn-off. Be aware that this is an issue. The 2010 spec requires that studs do not extend more than 1.5 inches above the top of the steel deck. And when you specify the length of the stud, when they weld it down, it is going to get shorter. When you weld it through bare steel, it shortens by about 3/16 of an inch. And when you weld it down through deck, it shortens all the way up to 3/8 of an inch. So I would recommend that you specify the installed length of studs on your drawings so that they order their studs to take into account this burn-off value, and you don't end up with studs that are shorter than the minimum requirement. One note, if you ever run into the situation where you have to deal with welding shear studs to a galvanized beam, it's generally not recommended because it creates some hazardous fumes and some inclusions in the weld. AIC Design Guide 18 recommends that you actually remove the affected coating, or you mask off these areas at the galvanizer. AIC's done a bunch of research on it. What I generally see happen, what the American Galvanizers Association recommends, is that you plan on welding 2 studs. So you weld 1 stud on there to burn off the galvanization. You give it a bend test. If it works, it stays. If it flies off, then you weld a second stud right where that first one was, taking advantage of the fact that the galvanization was burned off during the first stud shot. Number 9, the 80% rule. All I'm saying here is that in order to not violate the anchor length requirement and the specification, that there be at least a 1/2 inch of specified concrete cover above the top of the steel-headed stud anchors, you should consider only cambering 80% of the pre-composite dead load. So this is in recognition of the fact that your simple supports, so even a shear tab, has a certain amount of rotational resistance. So if you camber out 100% of your computer model's pre-composite dead load, you're probably going to over-camber that beam, and you run the risk of your studs sticking out of the top of the concrete slab, which is not where you want to be. And finally, number 10, to consider alternates to deck welding. I like pins. Hilti produces them, NewTek produces them, Simpson produces some screw anchors. I like them because I find that they have a higher quality control. They are easy to install in a rapid fashion. They're well suited for high sloped roofs. AWS actually limits puddle welding on roofs that are higher than 15 degrees, and SDI issued a position statement in 2012 that actually reiterates this issue and saying that you should use some sort of mechanical fastener for a highly sloped roof. So overall, if I have a job that's large enough to warrant it, I certainly would recommend you considering using mechanical pins in lieu of traditional puddle welds. So that takes us to the end of the presentation. We've looked at conduits, penetrations, openings, composite beam strengthening, and then sort of a hodgepodge of tips. And I'd like to thank Bo Dowswell for his information and help with the composite beam strengthening portion, as well as Don White for our discussions on compactness criteria. With that, I'll turn it back over to Christina.
All right, thank you very much, Will. We have a few questions from our participants, and just as a reminder, if you have not yet entered your question into the chat, you may still do so. So for our first question, I'm going to take us back to slide 53. The question is, can you use the stud on the girder when computing the sectional capacity?
No.
I believe they're referring to this stud there.
Yeah. No, I should not have. You should be using the stud on the beam.
Okay. Great, thank you. And the next question is, do you recommend the use of steel fiber reinforcement to reduce cracking in composite slabs?
Absolutely. Generally, that's the standard in our firm. You have to delve way down the rabbit hole of macro and micro fibers and steel versus polymer. That's a whole nother webinar in itself. But the concept of using some sort of distributed type reinforcing in the mix to help limit crack control as opposed to welded wire fabric is one that I wholeheartedly recommend.
Great, thank you. For our next question, I'm going to take us to slide 135, where you were referring to this ASCC position statement 23. Does this position statement on contraction joints give reinforcement percentages?
It does not. It doesn't actually give reinforcement percentages that it recommends. It's just a general discussion on whether contraction joints are useful or even needed in elevated slabs. To get dosing amounts, for instance, of polymer, microfibers, or steel fibers, you would need to actually talk with the fiber manufacturers to see what a reasonable dosage would be to help limit shrinkage cracking.
Okay, great, thank you. Next question, I'm going to take us to slide 31. And this is, I guess, kind of a concrete question, but why would you not just extend the straight bars beyond the edge of the opening? A distance,
because it's
LD.
Yeah. It's really best to try to cross perpendicular to where the crack's going to open up. So in this case, the cracks are emanating out from the corners of this this member. So you can either use a straight bar that is orientated 45 degrees, such as a straight bar right here, here, and here. In this case, you get the best of both worlds because we're providing some flexural reinforcement along the edges, and then that same flexural reinforcement, when turned and extended out as shown, is also quite effective in resisting this diagonal crack.
Okay, great, thank you.
Mm-hmm.
Next question. Are you familiar with any software that you'd recommend to use for designing and for reinforcing composite beams?
That's two questions. I am familiar with many types of software used for designing composite beams. I am familiar with no software for reinforcing composite beams. So I generally do reinforcement of composite beams by hand.
Okay, great. The next question we have is on camber.
Mm-hmm.
What would you suggest as criteria if the specified beam camber on the documents does not come out upon concrete pour? What thickness of concrete limits would you stop at for deeper or shallower conditions?
So I think what he's talking about there is where you don't have the specified cover if the camber doesn't come out. There's been some test run where the anchorage extended all the way to the very top of the concrete, so it had zero cover, and it really had no effect on the strength of the member. So the only thing that you really need to be careful of in that is maintaining things like fire rating So as far as the strength issue, it's okay to violate that limit in an in-place condition, and that's why the specification is pretty clearly worded that it is a detailed 1.5 inches. So indeed, if it doesn't, or a 1/2 inch, if it doesn't come out, then it's okay up to a point. Obviously, if they're sticking out of the slab, then you've got other issues.
Okay, great. And we have one last question. I'm going to take us to slide 161. The question is, do the mechanical fasteners provide the required attachment of the steel deck to the beam?
Normally, I count on the shear studs to provide that attachment. So the fasteners are really at perimeter conditions, or if I don't have enough shear studs to weld the deck down at the minimum requirement, then they're in between the shear studs. But the shear studs take the place of puddle welds or deck fasteners.
Okay, great. Unfortunately, that's all the time we have today for questions. If your question did not get answered, we'll try to reach you by email with a response.